Magnetic flux is a very important concept in physics, especially in the study of electromagnetism. It helps us measure how much of a magnetic field passes through a certain surface. You can think of it as counting the number of magnetic field lines that go through a flat area or surface. The more magnetic lines that pass through, the greater the magnetic flux. This is similar to how much sunlight passes through a window. A bigger window or more direct sunlight means more light gets in. Similarly, in magnetic flux, the size of the surface and the angle at which the magnetic field lines hit the surface both affect how much flux there is. Magnetic flux is denoted by the Greek letter phi, written as phi. The standard unit used to measure magnetic flux is called the Weber, with the symbol Wb. 1 Weber is defined as the amount of flux when 10 to the power of 8 magnetic field lines pass through a surface. The formula for magnetic flux is phi equals B dot A, which is the dot product of the magnetic field and the area vector. In simpler terms, this formula can be expanded as phi equals B times A times cos. Here, B is the strength of the magnetic field, A is the area of the surface the field passes through, and theta is the angle between the direction of the magnetic field and the direction that is perpendicular to the surface. This is called the area vector. When the magnetic field is perpendicular to the surface, that means it passes straight through. The angle theta is 0 degrees, and cos is equal to 1, so the magnetic flux is at its maximum. On the other hand, if the field lines run parallel to the surface, that is, at a 90-degree angle to the area vector, then cos becomes 0, and the magnetic flux is also 0, because no field lines are actually passing through the surface. The diagrams in the image help visualize this. They show how magnetic field lines interact with a flat surface and how the angle between the field and the area vector influences how many lines pass through. Understanding magnetic flux is especially important in technologies like electric generators and transformers. In these devices, changing magnetic flux over time creates an electric current, a phenomenon explained by Faraday's law of electromagnetic induction. So in summary, magnetic flux is not just a number, it tells us how strongly a magnetic field is interacting with a surface, and it's a key idea in how we produce and use electricity in the real world.